I can fight monsters, I can't fight physics.
So this is a Young Modulus question from 2016, paper 1. So figure 5 shows a tensile stress strain graphs. So first thing we know about them, the gradient is equal to the Young Modulus, and the area is equal to the work done per unit volume. So those are your facts. So statewise meant by tensile stress and strain, so they're just the formulas. So it's the force per unit cross-sectional area. So that's nice and easy. And the next one, strain, let me just scroll up, is the extension per unit original length, or per original length, probably easier, brackets. Okay, this one has no units, and this one has units of newtons, meters minus 2, or pascals, which is the same as the units for Young Modulus. Right, so let's look at these graphs in a bit of detail, though. So what we got these three graphs. They've got a large Young Modulus because they've got a large gradient, so they're quite stiff. Okay, so they're quite taut. Okay, so they don't stretch much. These two, if you look at these two, they have a large UTS. Okay, so they can withstand a large force. And this one has a large plastic region. Okay, or in fact, it has a small Young Modulus also. So that means it's quite elastic rather than stiff. Okay, so you should be able to get all that information from the graph. So just things that are obvious. And of course, don't forget formula for Young Modulus is stress over strain, which if you put all the units in, is FL over AX. And don't forget F over X is K, so KL over A. So these are all your go-to knowledge. Let's have a look at the next bit then. So identify a property of material A using the evidence. So we could have just said it's got large Young Modulus, or it's very stiff because it's got a large gradient. But let's look at what else it's got. It's also got no plastic region, so it's actually what we call a brittle material. So it's brittle because there's no plastic region, okay, or on the graph. So it goes straight to breaking stress without bending of any sort. So then it says a cylindrical specimen of material A under test has a diameter. Now, where do we use this? We use this in the area, which is pi r squared, which is pi d squared over 4. And a breaking stress of, so that's equal to 1.3 times 10 to the 9 pascals, which is equal to your stress, which is equal to force over area. So I think I pretty much answered it. Work out F. Okay, so what do we know? We know 1.3 times 10 to the 9. The stress is equal to force over the area. So the area is pi times d, 1.5 times 10 to the minus 4 all over 4. Okay, so we can work out F. So F is 1.3 times 10 to the 9 multiplied by this area. Let me just quickly work it out. No, sorry, I forgot to square that. All right. So that is equal to 1.77 times 10 to the minus 8. Okay, so if you put all that in, so 1.3 times 10 to 9 times answer, so that gives me 23 newtons. Okay, so that's nice and easy. So now let's look at the next part of the question. So discuss which of the four materials shown on the graph is most suitable for each of the following applications. So you've got the cable supporting a lift in a building and a rope, let's call that one, and a rope or cable attached to a spring during a bungee jump. So what do you need for a cable supporting a lift? It can withstand large force. I should probably write this. And also it's got to be stiff. You don't want it to be springy because it'd be a very uncomfortable ride going up or down. Whereas a rope what do you want from this bungee rope? You need it to be able to be elastic, not stiff. Okay, so that's the most obvious thing. Okay, um, so therefore you need it to have a smaller Young modulus. Hopefully that should be able to inform your answer. And so let's look at the first one. So I'm going to split the page in two. So you got number one. What do we need? So I should have just wrote that here. So we would probably use B from what I can see. So why? Has a high Young modulus and it has the largest UTS. So we'd use B because it has a large UTS before it snaps and it has a large Young modulus. You would not use A because A is too brittle, so it would snap before even you had a little bit of give, so it just snaps straight away, which would be pretty fatal. So A, B. So now, would you use C? C, no, because it has a lower ultimate tensile stress, so you can't withstand as much force. Would you use D? No, because it's got a low UTS or breaking stress as well. So that's dangerous. So that's the argument for this one. You don't have to write loads and loads. Now for the rope, I would probably use, so for number two, I would use D. Now, why is it D? Is because it can stretch further, and that's what you want a bungee to do. You want it to stretch before fracture. Okay, you do not want it to be brittle, so you can see why. And therefore, because it can stretch further, it can store more elastic energy, which is important because you want it to spring back up. You would not use A. Why would you not use A? Because, in fact, you wouldn't use A, B, or C because they have a high Young modulus. That means they're too stiff. If they're too stiff, they're not going to stretch. If they don't stretch or they snap before they stretch, they're going to snap and then you're going to fall into whatever it is you're landing on. Okay, so that would be sort of the majority of it. In terms of anything else, you could probably say they have small strain, all three of them. They also have small strain, so they don't stretch a lot. Okay, we need it to stretch a lot, and so on. So that would probably be what would get you the 6 marks here. Okay.